valence shell electron pair repulsion theory. Let's begin. Have you seen a balloon vendor at his art? He blows up a few balloons, ties them together, gives a twist here and a twist there, and a beautiful shape emerges. Similarly, nature's building blocks, the atoms, combine chemically in a variety of permutations to form molecules with diverse shapes. The three-dimensional arrangement of atoms in a molecule is referred to as its molecular geometry. Many properties of a substance can be attributed to its molecular geometry. Can the molecular geometry of a molecule be predicted? Yes, the molecular geometry of a molecule can be predicted with the help of the valence shell electron pair repulsion theory, or VSEPR theory. What is valence shell electron pair repulsion theory? How does it help to predict the shapes of molecules? Come, let's learn about the VSEPR theory in this module. What you will learn. At the end of this module, you will be able to describe the concept of the valence shell electron pair repulsion theory. Apply the VSEPR theory to predict the shapes of molecules. VSEPR theory, predicting the shapes of molecules. Electrons are the negatively charged particles of an atom. Electrons that can take part in chemical bonding are known as valence electrons. These are found in valence shells, which are the outermost shells of atoms. A chemical bond involves either the transfer or sharing of valence electrons between atoms. The sharing of valence electrons between atoms in a molecule can be represented by Lewis dot structures. A Lewis structure or Lewis dot diagram is a type of shorthand notation which depicts the distribution of valence electrons in molecules. It shows the number of valence electron pairs in each individual atom, including the bonding electron pairs and the non-bonding electron pairs, also known as lone pairs, that may exist in the molecule. Sharing of electrons between atoms gives rise to covalent compounds. Molecules of covalent compounds come in many shapes and sizes. The shape of a molecule can be predicted using the valence shell electron pair repulsion VSEPR theory. The VSEPR theory assumes that the arrangement of valence electron pairs around the central atom in a molecule determines its molecular geometry, that is, the molecular shape. How do we use the valence shell electron pair repulsion theory to predict the shapes of molecules? To understand this, let us first consider the assumptions made by the VSEPR theory. 1. Valence electron pairs in an atom repel each other. 2. Valence shell electron pairs, therefore, arrange themselves around the central atom in such a way that there is minimum repulsion between them. This happens when they are as far apart as possible. For example, if there are two electron pairs or electron groups, then these adopt a configuration where the electron pairs are at an angle of 180 degrees, as in beryllium hydride and carbon dioxide. 3. It is this definite arrangement of electron pairs that gives the molecule its distinct shape and geometry. In other words, molecular geometry depends on the electron pair geometry. 4. A non-bonding electron pair or lone pair exerts greater repulsion than a bonded pair. So, lone pair repulsion is greater than lone pair bonded pair repulsion, which is greater than bonded pair repulsion. 5. For the purpose of determining electron geometry, the two pairs of electrons of a double bond and the three pairs of a triple bond are treated as one pair. Let's take a look at the possible geometrical shapes that arise when there are different numbers of bonding and non-bonding pairs of electrons surrounding an atom. When there are two electron pairs, the possible molecular geometry is linear. When there are three electron pairs, the possible molecular geometries are trigonal, planar, or bent. When there are four electron pairs, the possible molecular geometries are tetrahedral, trigonal pyramidal, or bent. When there are 5 electron pairs, the possible molecular geometries are trigonal bipyramidal, seesaw, T-shaped or linear. When there are 6 electron pairs, the possible molecular geometries are octahedral, square pyramidal or square planar. Shown here is a chart which depicts the possible VSEPR molecular geometries. Take a look at it again. VSEPR strategy. Let us now use the VSEPR strategy to predict the shape of a water molecule. First, draw the Lewis structure of the water molecule. Count the total number of electron pairs around the central atom oxygen in the molecule. Determine the number of bonding electron pairs and non-bonding electron pairs or lone pairs. A water molecule has 2 bonding and 2 non-bonding electron pairs surrounding the central atom, making a total of 4 electron pairs. The most stable spatial arrangement of the valence electrons is one in which the mutual repulsions are minimum. Remember that if there are 4 electron pairs around the central atom, the electron pairs experience least repulsion when the arrangement is tetrahedral. So, arrange the 4 electron pairs around the oxygen atom in a tetrahedral configuration. However, this is not the final structure, as the electron pairs are not similar. The effect of the lone pairs has to be brought into the picture. The presence of the lone pairs distorts the shape. The lone pairs exert greater repulsion on the bonded pairs, resulting in the bonded pairs being pushed closer to each other. Next, determine the molecular geometry. To do this, only the atoms need to be considered. So, ignore the lone pairs and look only at the arrangement of the atoms. We observe that the atoms are arranged in a bent or V shape. Alternatively, once the numbers of bonded and lone pairs have been determined from the Lewis structure, the shape is identified using the VSEPR molecular geometry table.